A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the idea of rotations and compatibility. So let us get started. So for the topics for today, first we'll start with a discussion on differential displacements, and through that we'll talk about rotation tensors and rotation vector. This will be followed with a discussion on compatibility, which is one of the most interesting ideas in kinematics in continuum mechanics. So let's get started. So here is the typical picture that we draw for 1, the undeformed configuration, and 2, the deformed configuration. So we have a point capital P around which I want to quantify the deformation, and point capital Q is a point that is close to point P in the undeformed configuration. So first we draw the vector d capital X that joins capital P to capital Q, and then small p and small q are the images for capital P and capital Q in the deformed configurations. So we draw the vector small dx, and the displacement of point P is denoted by u super P, and similarly the displacement for point Q is denoted by u super Q. And then we say that since Q is close to point P, the displacement of Q will be slightly more than the displacement of P. So this differential displacement vector is the difference in the displacement of Q from the displacement of P. So this is also called the relative differential displacement. So to see the relative differential displacement, or just the differential displacement du, we draw a parallel vector to d capital X in the deformed configuration, and then we write d capital X plus du is d small x, because u is defined as small x minus capital X, so du becomes d small x minus d capital X. Now a better way to visualize this differential displacement is to sit on the particle P and then make the measurements. So let's say this is the body and you have a particle P, the material particle P. So you sit on it and you find that point Q was here. So you measured the d capital X vector like this. And now since you're sitting on particle P, the body deforms and you find that now the particle Q looks like this. So you'll measure the displacement of this as d small x. And what you see is that now the differential displacement is the displacement of the particle Q as you saw it while sitting on the particle P. So this enforces the idea of the relative differential displacement. Now motion can be characterized as a translation, a rotation, and a deformation. And deformation includes both stretching and shearing. So our interest today will be in rotation. But for that, we'll have to link the idea of a differential displacement, which is resulting due to a pure rotation. Now, when we talk about differential displacements, the information about translation is lost. Because if we think about translation, what happens is, for example, in this picture, if you're sitting on the particle P, you will not see the particle Q moving at all. So the du, or the relative differential displacement of the particle Q with respect to particle P, will be 0. Remember, when you sit in the particle P, you sort of sit slightly above it, so you don't rotate with the particle P. That's very important here, because if you rotate with the particle P, then even the displacements due to rotation will be lost in the measurement. So we are sort of hovering above the particle P so that we stay above it, but we don't rotate with the particle P. And this is just for understanding. So I'll just mention that translation information is lost because of the differential displacement. Translation is basically you add a constant to the component, for example, capital X1 plus some C1, capital X2 plus some C2, and capital X3 plus some C3. So all that is lost when you differentiate the small x value. So dui, that's the differential displacement vector, in the initial form is written as partial ui by partial capital Xj times dxj. And this quantity, by the way, is defined at the point P, because we are interested to figure out what's happening around the point P. So all deformation gradients, displacement gradients, and strain tensors are written at the point P. And this is the reason whatever we find out is the information about the deformation in the neighborhood of point P. We can't go too far away from point P, because then we won't have a dx, we'll have a finite distance from particle P. So this quantity, which is del ui by del capital Xj, by the way, in the infinitesimal deformation theory, we discussed that this can be written as del ui by del small xj. So I can call this as ui comma j. So we are working in the infinitesimal deformation for this discussion today. And as I said, mostly we'll be discussing in terms of the infinitesimal deformations unless I mention otherwise. So this displacement gradient tensor ui comma j can be written as a sum of a symmetric part and a skew symmetric part. Let's do that. So we know that if you have a matrix Aij, then we can always do an additive decomposition where we split it into a symmetric part and a skew symmetric part. So in a similar fashion, we can write this tensor ui comma j as a symmetric part, which is the sum of ui comma j plus uj comma I divided by 2, and a skew symmetric part ui comma j minus uj comma I upon 2. And you can see that this actually is ui comma j. So I leave it to you to check that this is symmetric and this is skew symmetric. And the symmetric part we already have discussed, that's the epsilon ij, which is the infinitesimal strain tensor. And this skew symmetric part is something that we'll discuss today, and that is denoted by omega ij, which, as you may have guessed, is called the rotation tensor. Or to be more specific, it's called the infinitesimal rotation tensor. So what that means is that if epsilon ij is 0, then the motion is a pure rotation. And we have somehow shown that in the past when we discussed in terms of finite deformations, where we said if the Lagrangian finite strain tensor was 0, it was a pure rotation. So for this infinitesimal deformation, if epsilon is 0, then omega ij contains all the information about deformation, and that is a pure rotation. So let us see what this omega ij tensor looks like. So omega ij is skew symmetric. So what that means is that omega ij is minus of omega ji. So from this logic, I can see that the diagonal terms of omega are 0. And then what I'm left with is the off diagonal terms, but it is also skew symmetric. So that means omega 1 2 is negative of omega 2 1. So omega 2 1 can be written as minus omega 1 2. This is omega 1 3. So omega 3 1 is minus omega 1 3, and omega 2 3 is minus of omega 3 2. So omega 3 2 is minus omega 2 3. And now you can see that we have three distinct scalars that exist in the rotation tensor. So that is interesting because this rotation tensor omega ij has only 3 or up to 3 non-zero scalar values. So intuitively speaking, we have a feeling that we can associate a vector with it in 3D because we only have 3 scalars that characterize rotation in this tensor. And this idea of a vector being associated with omega ij is more general mathematically speaking. That is, every skew-symmetric tensor has an associated vector with it. So for this case, we can write the vector omega tilde I is half epsilon ijk times the omega tensor kj. So I'm using the same symbol with the tilde just to denote that this is the associated or the corresponding vector to the omega tensor. And as I said, this idea is more general. So this idea of a vector being associated with a skew-symmetric tensor is called a dual vector of the skew-symmetric tensor. In this case, that's omega ij. So we can see that rotation, which was described by a second order tensor, although a skew-symmetric one, can now be described with a vector. So this is giving us a hint that rotations are vectors, which we already know, by the way, but this is discussing that through a new perspective. So given an omega tensor, which is skew-symmetric, you can find an associated dual vector that's called the rotation vector, and we can invert this. That is, if I know the rotation vector, I can find the corresponding rotation tensor. So omega ij tensor can be written as minus epsilon ijk times omega k tilde. So we will show this as a part of a tutorial or an exercise in the course, and for now you can assume it's true. So using 1, I can write my rotation vector. Let's call it rotation vector as half epsilon ijk, and then I'll substitute the definition of omega that we just found out above. That's half u k comma j minus u j comma k. So expand the terms, and now what I'll do is I will replace j with the k and k with the j in the second mathematical term here. So this becomes this simply is index manipulation. So now we see that these terms are the same. So we'll try to bring the indices of the second epsilon also the same as indices of the first epsilon. So I can say that epsilon ikj is negative, so this becomes a positive of epsilon ijk. So swapping any two indices of epsilon changes the sign. And this becomes half of epsilon ijk times u k comma j. Now if I look at this thing, I can see that this in the symbolic notation denotes the curl of the vector u. So the omega tilde vector is the curl of the displacement vector u. So for a purely 2D case, if I write the omega vector as half times the curl of u, that simply becomes a vector purely in the E3 direction. Now when I said 2D, what I meant was that your displacements, both u1 and u2, are in the x1 x2 plane. So that means they are purely a function of x1 and x2, and they do not depend on third coordinate x3. It's like you have a two-dimensional plane and the body can deform or the points can move in this plane. The plane cannot warp. So this is what we get by simplifying this 2D case for the rotation vector omega. So if motion is happening in a plane, then that means the points can move in the plane. So the rotation is about the E3 axis. And this again reinforces the idea that in a plane, rotation vector points outside the plane of paper. So all this intuition that we have developed is nicely packaged into a theory now. Right, so now we understand about the rotation tensor and the corresponding dual vector, that is the omega tilde vector. That's called the rotation vector. So let's take the case that if your epsilon ij is identically 0 everywhere in the body, then the displacement dui is ui comma j dxj, and ui comma j, the displacement gradient tensor, is simply the rotation tensor omega ij because strains are 0. So from this relation, I can write my omega ij as epsilon ijk omega tilde k with a negative sign. So this becomes minus epsilon ijk omega tilde k times d capital X j. And you can see that in the symbolic notation, this is nothing but the cross product of omega vector with the dx vector. So our differential displacement is the cross product of a rotation vector with the displacement vector in the material configuration. So let's see what this denotes. So we have a point P, or a point small p. As we said, we'll be hovering above the point P so that all displacements are relative. And we had the point Q here, so that this was our d capital X. And in this 2D plane, let us say this is a planar motion, our omega tilde vector is coming out of the plane of paper. So omega cross dx, so I'll say omega is some constant times E3 hat in this case. So omega cross d capital X is a vector which is perpendicular to this vector, and this is our du. And you know that in the case of pure rotation, the displacement is perpendicular to the radial vector. So our d small x will look something like this, and this we call d theta. So if you have a line element d capital X and you provide a displacement which is perpendicular to d capital X all the time, that means d capital X simply is rotating. So therefore, this is the case of pure rotation. So whatever I mentioned to you has been shown now that omega tensor omega ij corresponds to a pure rotation case. And of course, if omega ij is 0, this implies it's a pure strain case. That means that there is no pure rotation. All we have is stretching and shearing. So stretching is where the sizes change, and shearing is when the angles between two perpendicular elements will change. Right, so this completes the first half of today's discussion, which was on infinitesimal rotations and the corresponding rotation tensor and vectors. The second part of today's lecture will be on compatibility. Now, compatibility in continuum mechanics is a very interesting and a deep topic, but the idea is very straightforward. So for the discussion for today, I'll be focusing on the idea of compatibility. Given that this is a foundational course, you will go deeper into it by solving the equations of compatibility along with the other differential equations. But for today's discussion, I will introduce the idea of compatibility and the equations of compatibility to you. Now we've been writing epsilon ij or twice epsilon ij as ui comma j plus uj comma I. So sort of we are trying to find the components of epsilon for a given displacement vector field. But there are situations where you have the strains available to you. Let us say you measure them as an experiment and you would want to find the displacement field that results in that strain. So the problem is like this, where the left hand side contains derivatives of unknown displacements and the right hand side has known values. Now epsilon has 9 components, so we should have 9 equations here, but since it is symmetric, we have 6 differential equations. But the displacement is a vector, so we have 3 unknowns. But of course, these unknowns are u1, u2, u3, which are functions because we're talking about fields. But nevertheless, we need to find out 3 unknown functions, one for each component of u. So in a way, we have 6 equations and 3 unknowns. So it does seem an overdetermined system because we have more equations than the unknowns. Of course, these are not linear equations, these are differential equations. So we can state that the 6 terms of epsilon cannot be arbitrary in the sense that they need to guarantee the existence of a displacement field which comprises 3 scalar functions. So there has to be some relationship between the terms in the strain tensor. So compatibility, or the equations of compatibility, are nothing but this relationship between the terms of the strain tensor. Now, most of the books in continuum mechanics will simply give you the equations of compatibility at this stage. But given the foundational nature of this course, I would want to motivate as to how you get these equations of compatibility, that is, the equations that relate the different terms in the strain tensor. If you recall from the mathematics discussion that we had in the beginning of the course, we can define the curl of a second order tensor, that is epsilon in this case, as the permutation symbol epsilon ijk. Now we'll be dealing with two epsilons. One is this epsilon, which denotes a permutation symbol, and the other is this epsilon, which denotes the strain tensor. So while writing, I'll be calling this as an epsilon and this as a strain. But when I write them, they look different. So the curl of strain is epsilon ijk, strain qk, comma j. So we can see that there are two free indices in this because the curl of a second order tensor is also a second order tensor. Now with this definition of curl, we also write this as the symbol nabla cross strain. So with this I can write the curl of strain tensor in the initial notation as epsilon pqr times epsilon ljk times strain rk comma jq. So I leave it to you to show this using the definition of curl of a second order tensor. So this is going to be a good exercise for you in indicial notation and tensor calculus. So let's call this equation A because this is something we'll be working with. And now I'll substitute the definition of the strain tensor in A. So that will give us the curl of strain as this. Now we'll open the brackets. So we get these two mathematical terms. Now let's look at the first term. So what we see from here is that k and j are after the comma. That is, we are differentiating ur with respect to del xk, del xj and del xq 3 times. We agree on the fact that since the derivatives of u are continuous, so the order kj in the derivatives does not matter. It's a mixed derivative, the ordering can change. So this means that this quantity is symmetric in the indices k and j. And now let's look at this epsilon. From here you can see that this is skew symmetric. So this whole quantity is skew symmetric in k and j. And we have shown in the past that if you have a product of a symmetric and a skew symmetric tensor, then that is a 0. So this turns out to be 0. And similarly, in the second term, we have indices r and q. So the derivative of u term in the second mathematical term is symmetric in r and q, and we have an r and q here in the epsilon, so this is skew symmetry. So this again goes to 0 by the same logic. We have shown that the curl of strain tensor epsilon is a 0. And that basically is a relationship between the different terms of epsilon. So let's write this in the initial notation again. So we had epsilon pqr, epsilon ljk times strain rk, comma jq. Now I'll underline the free indices in this expression. So we can see that p is a free index and L is a free index. Q, R and J, K, they are repeated. So this can be written as a CPL, which is like a second order tensor. So a second order tensor has 9 terms. That means we have a total of 9 terms. And since this thing is a 0, that means we have a total of 9 equations. Because you have repeated indices, when you expand the terms, you will get a relationship between the derivatives of different terms of epsilon. So these are the 9 equations we were looking for. Actually, there are 6 equations, not 9, and that is because CPL is CLP. So just like a symmetric second order tensor has 6 unique components, we have 6 unique equations. So this implies you have 6 equations of compatibility. So again, this is an exercise in index manipulation. I will leave it to you to show that CPL is symmetric. So that's another homework for you to try out, and that will be a good exercise in indicial notation. So these are the 6 equations of compatibility. What I'll do is I will just show you how to get one of the equations. In fact, let us say if we are dealing with a plane strain situation, so in that case, you only have epsilon 1 1, epsilon 2 2 and epsilon 1 2 as the 3 non-zero epsilons. So it's only one compatibility equation that is required, and just for the sake of an exercise, I will right now demonstrate to you how we get this equation of compatibility between these 3 terms using this equation which contains all the 6 compatibility equations. So what we'll do is we will take P equal to 3 and L equal to 3 in equation B. So the left hand side of B is denoted by CPL, and we are taking P and L both equal to 3 to get one equation of compatibility. So this becomes epsilon 3QR epsilon 3JK times strain RK comma JQ, and this is equal to 0. So let's first expand over the indices Q and R. Now we know that if any two indices in epsilon are repeated, it's a 0. So we have only two combinations here, epsilon 312 and epsilon 321. So this is for the case where Q is 1 and R is 2, and this is for the case where Q is 2 and R is 1. So let's write the other terms. This is epsilon 3jk, and this strain R is 2, K comma J, Q is 1, plus then R is 1 here, K comma J, Q is 2. Right, so now we have these two indices J and K. So each one results in two cases. So we'll have a total of 4 terms. Let's call these 1, 2, 3 and 4. This is a 0 by the way. Now epsilon 312 is a 1, so I don't need to keep writing it. I'll simply remove that here. So we have epsilon 3. Now we'll take J equal to 1 and K equal to 2 in this case. This becomes epsilon 312 times strain 2, K is 2 now, and J is a 1. So this is the first term. And the second term is epsilon 3. Now I take J equals 2 and K equals to 1. So this becomes epsilon 3, and then J is 2 and K is 1 times strain 2, 1 comma J2. And this, by the way, simplifies. So epsilon 312 is a 1. So this is strain 2, 2 comma 1, 1. And the second term is epsilon 321 is a minus 1. So this is a negative strain 2, 1 comma. So there was a mistake here. So this was J1. So J is a 2 and then we had a 1. So this is a minus epsilon 2, 1, 2, 1. So now we have got all the 4 terms now. So let's add them together. So this is epsilon 2, 2 comma 1, 1 minus epsilon 2, 1 comma 2, 1 minus epsilon 1, 2 comma 1, 2 plus epsilon 1, 1 comma 2, 2, and that's a 0. And you see that epsilon 2, 1 is the same as epsilon 1, 2, and the order in differentiation also doesn't matter. So these terms are the same. So this becomes epsilon 2, 2 comma 1, 1 plus epsilon 1, 1 comma 2, 2 minus twice epsilon 1, 2 comma 1, 2, and that's a 0. So this is one of the compatibility equations, and for a plane strain situation, this is the only compatibility equation we are interested in. So you see that you cannot put arbitrary functions in the different terms for the epsilon field. They have to be related through this compatibility equation. I hope that you appreciate the idea of compatibility, and you also appreciate how we get to these equations, where for us the starting point was the curl of epsilon, which came out to be 0 for the definition of epsilon in terms of the symmetric part of the displacement gradient tensor. So this compatibility was shown for an infinitesimal strain tensor epsilon, but when the motion is finite, then it is the deformation gradient tensor F that is of interest. So I'll simply write down the compatibility requirement for a finite deformation case. And the condition is that the curl of the deformation gradient tensor F has to be 0, which tells us that the terms of F are also not completely independent. There is some relationship between them. We will show this in the tutorial this week. So this brings us to the end of this lecture today, where we started our discussion with a discussion on the rotation tensor omega ij, which helped us understand infinitesimal rotations, which can also be represented using rotation vectors because of the fact that omega tensor is skew-symmetric. And then we talked about the idea of compatibility, which is key to obtaining displacement fields in continuum mechanics. So thank you very much, and I will see you in the next lecture.